Hi friends, how do we evaluate the retrieval accuracy of an embedding model in a RAG system when we do not have the ground truth? In a previous video, we had the ground truth in the form of these question and the context pairs. For example, each of these questions can be answered using the corresponding context. So what we did is we choose an embedding model, we build a vector store, we ingest all these contexts, and then for each question we retrieve the top one document, which is here. All right. And then since we know the ground truth, meaning the right context, we simply counted how many times the embedding model is able to retrieve the right context for all these questions, right? That gives us the retrieval accuracy of an embedding model. To find the best embedding model, we did the experiment using a bunch of models and we compare the performance. Now all that was possible because we had the ground truth in the form of the question and the context pairs. Now let's assume a scenario like in a real world, we do not have this ground truth unless it is manually created or created with the help of an LLM. All right. So we have a bunch of documents. We build a RAG system. Now we want to evaluate the retrieval embedding model performance. We do not have the ground truth. Let's see how we do that in this video. All right. A bunch of Python libraries, and we will be using a bunch of embedding models using Ollama. For this, we are using this dataset called RAG Dataset 12,000. So it has these triplets, the question and the context using which the question can be answered and the right response. So this dataset is prepared for evaluating and testing RAG systems. But for today's case, let's assume we do not have these pairs, right? We do not have the ground truth for evaluating the embedding model retrieval performance. All right. So we will be testing a bunch of embedding models, and some of them have the context length as low as just 512 tokens, right? Unlike LLMs, which have the context length of millions of tokens, embedding models are generally 3 to 4 orders of magnitude smaller, and they have the context length of only a couple of hundreds to a couple of thousands. So we use this tick token just to count the number of tokens in each context, which is what we see here. And then we filter out all the records which have the context length higher than 350 just to be on the safe side. All right. Okay. So we have the context and the questions. The key here is we are not going to use them as pairs. All right. So we will be testing these 7 embedding models. Now these are from different developers, and these are the most commonly used embedding models on Ollama as well as Hugging Face. Now if you want to test more models, here are some suggestions. All of them are available on Hugging Face for free. All right. Now let's look at some metadata of these embedding models. All right. So using this Ollama show, we can access the metadata of all these models. So for these models, we have the context length, the embedding size, and the parameter size. So as you can see here, the number of parameters is as small as just 33 million to 560 million. Whereas for an LLM, this would be billions, right? At least 1 billion all the way up to trillions. So the embedding models are typically 3 to 4 orders of magnitude smaller in size. And as I mentioned, the context length is as small as just 512 tokens. Okay, that's the reason why we have filtered out the records with larger context length. And then the embedding size, this is also typically a couple of hundreds to a couple of thousands. All right. So what we do is we take one embedding model at a time. We build a vector store. We compute the embeddings. We ingest all the embeddings as well as the corresponding context into it, and then we store them or persist them on our disk. Okay, we are looping over all the LLMs. All right, we access all the embedding models. We access the embedding models using Ollama embeddings, and then using the Facebook FAISS vector store. Here we provide all our context. We are providing these 1000 contexts. Here is our embedding model. So this will compute the embeddings for all our contexts. All right. And then we are just tracking the processing time for each embedding model. And here we are persisting the vector store to our local disk. Okay. So this is how it looks like. So within this vector store, within this folder, we have saved these 7 folders corresponding to each embedding model, and each folder contain these 2 files. Let me run this. BG, I think it is BG. Yeah, it will contain these 2 files, index.faiss and the pickle file, which contain the embeddings and the corresponding context. If you just look at the processing time to create embeddings for 1000 documents plus ingestion, the biggest model, the Snowflake model, took around 250 seconds, whereas the smallest model, which is this MinLM with only 33 million parameters, it took about 100 seconds. All right. Now, so here we have already created our vector stores, right? Now what we do is we read the vector stores from the disk, and then for each embedding model, for the 1000 questions we have, we retrieve the most relevant context. Okay. So again, looping over all the embedding models, accessing the embedding model. Here we load our vector store from the folders where we saved. And now we define the retriever. We want to retrieve only the top 1 documents. Now, typically for a RAG system, we might retrieve top 5, 10, or even 20 documents, depending on if we are doing re-ranking, etc. But in this case, we know for each question, we have only 1 relevant context, right? So for that reason, we are extracting only the top 1 document from the vector store. All right. Again, we are tracking the time of the processing times. But here, so we loop over all the 1000 questions we have, and then here we have the retrieved document. Okay. All right. So after running this, we would have this one, right? We would have a data frame where for each question, now for each embedding model, we have the top retrieved context. All right. In a previous video, in addition to this, we also had the ground truth, right? What's the correct context in order to answer this question? Now, in this scenario, we assume that we do not have the context, right? We do not know. For example, let's say we are building a RAG system using some policy documents or product documents. We divide them into chunks. We ingested them in the vector store. Now we have a bunch of questions, but we don't know which is the right context to it. That's the exact scenario we are trying to simulate here. All right. So we have the questions, and for each embedding model, we have the top retrieved document. Now here, since we do not have the ground truth, what we do is we use this concept of ensemble modeling in machine learning, and we go with the majority vote. So here we have used 7 embedding models, right? So what we do is whichever the context is retrieved more often by these 7 embedding models for a given question, we take that as a ground truth. Okay. So since we do not have the ground truth, we are going with the majority vote by using multiple embedding models. So for this method to work, we need a number of independent, the word key, the key is independent models here. For example, here we have a number of embedding models within this family min LIM, right? So if you look here, all right, as you can see from here, from this sentence transformer, all these embedding models belonging to the same class. Now in this process, if we use similar embedding models, because they work in a similar way, all of them will extract the same context, but that does not mean that's the right context. Okay, so that's why in this method we have to be very careful to choose the embedding models which are not correlated to each other, or which are not developed from the same developer using the same methodologies. Okay, so make sure the embedding models you are using, those are fairly independent, they work on different methodologies. All right, okay, so here we have the question and we have the retrieved context from 7 embedding models. And then what we do is we take these 7 responses and we find out which is the most common response. Okay, so this is just the processing time. So here what we are doing is we are simply finding out the most common among those 7 retrieved context. Okay, and we are also counting how often that occurred. Now sometimes there can be a tie, right? For example, here we have 7 embedding models. It could be that three of the embedding models, they pick one context, the other 3 pick another context, third one or the 7th one pick a different one. So we have a tie, right? So here we are eliminating all such cases. Only when we have a clear winner, we are taking that as a ground truth. Okay, all right. So once we run this, here we have created these 2 additional columns. So this is the voting winner. Okay, if you look at this TMZZ, so all 7 embedding models, I mean, this seems to be an easy case, have voted for the same context. Okay, and then here we can see the voting count. So 7 out of 7 models voted for the same context. Okay, so basically we are, by using multiple embedding models, we are sort of finding out what could be the most likely ground truth or the correct context. All right, so once we have that, it's easy. Now we can compare how many times the nomic embedding model retrieved context matches with the voting winner. Okay, which is what we are doing here. All right, so and then we converted this into percentages. So here we have the percentages. All right, if we plot, so this code is just to plot, and this is what we have. Now let's plot this models dot head models. Just a second. What's the data frame? df models dot head. I think I restarted my system. Anyway, doesn't matter. All right, so let's go back and see the models one more time. Okay, all right, so let's look at the parameter size. So the smallest model is this all min LM. So it has these 33 million parameters. It's almost 17 times smaller than the largest model, which is this Snowflake. And then the 2 largest models are this PGE large and with 333 parameters and mixed bag MXBAI embedding model. All right, so the performance is in accordance with the size of the embedding models. So even though this model is 17 times smaller, its performance is around 87%. So if we ask 100 questions, for 87, it is able to retrieve the right context. Okay, whereas the BGE model, that's the top performing model. So these three are the models with more than 300 million parameters. But if we exclude the MinLM, the 6 embedding models we have tested, they have accuracies over 90%. All right. These results, they align very much with when we had the ground truth, which is the results here. So this suggests that even if we do not have a ground truth, we can use multiple independent embedding models to find out what could be the most likely right context, and hence we can evaluate the performance of each embedding model. Now, this does not mean we don't need the ground truth. It's always gold standard to have the ground truth, make the predictions or retrieve the context and compare that against the ground truth. But we know the ground truth can be expensive. So if you cannot create the ground truth, maybe you can use this multiple embedding models method to evaluate and find out the best embedding model for your RAG system. Yeah, that's all for this video. Thank you very much. If you find this content useful, please support the channel. Thank you very much.